So yes, indeed, I will speak about fractured rock. So I know relatively well fractured rock since I'm field hydrogeologist and I work a lot in fractured rock hydrogeology. But today I would like to speak about heat transport in fractured rock. So the outline of the lecture will be about first an introduction about heat transport in porous media, just to give some idea about how this is treated usually, and then to give a bit of background about fractured rock hydrogeology that will be mainly on crystalline rock aquifer that are not porous and where flow occurs mainly in fracture. And I will present briefly also how you can use heat as a groundwater tracer, because it has been used for long and it's useful especially in this environment. And then I will speak about some, after having shown some simulation, some results, numerical modeling, some field tracer test experiments to try to understand what are the, in fact, the effect of heterogeneity in, on heat transport. So let's begin by heat transport in porous media. So if we consider heat transport in porous media, so this is, we had the nice presentation of geothermy this morning by Peter. And so now if we consider heat transport in porous media, what we have to do is that we have the fluid that transports heat. You have heat exchange between the fluid and the solid phase. This is supposed to be the solid phase, and then there is conduction in the solid phase. So usually, to treat this problem, what is done is to assume that there is a thermal, almost instantaneous thermal equilibrium between the temperature in the fluid and in the solid phase as the heat front pass into the porous. And so, according to some work, this time is close to the minutes, or if the size of the particle is really big, then it can be longer. But in porous media, usually, we assume that there is an instant equilibrium. In that case, what you can do is to apply the classical law we know already for transport and just replace the concentration by temperature and have a change of temperature to time that depends on an advection term and a dispersion plus conduction term. So this is what is classically done, and in that case, if the only thing is that you see this term, and in this term phi is the porosity, and 1 minus phi represents the solid phase, and then here you have just the heat capacity of water and the heat capacity of the rocks. Since you have some exchange, the velocity, in fact, of the temperature is not going as fast as, for instance, the velocity of a solute that is transported by the fluid. And in that case, if you, for instance, inject a pulse of heat on solute, what would happen is that simply you would have for the solute a dispersion in the porous media, while for the heat you will have conduction and dispersion, but you will have also a thermal retardation, since part of the heat is used to transfer into the solid media. And so you have the thermal retardation expression that is given here as a function of the property of the rock, fluids, and the porosity. One thing that I will not speak about is that in porous media you may have also another transfer process, not only advection and conduction, but you can have what we call free or natural convection, which is observed especially when you have a difference of temperature. For instance, in an aquifer, from the bottom from the top to the bottom of the aquifer, if the difference, if the gradient is too high, then in that case it can lead to free of natural convection. And in that case, to estimate if such condition may be pertinent for your system, people use the Rayleigh number for porous media, which is a function of thermal expansion of water, the heat capacity of water, K is the intrinsic permeability of the porous media, E is the thickness of the aquifer, and delta T is the difference of temperature. So the larger the difference, the greater the Rayleigh number. And if the Rayleigh number would be larger than this number, which is approximately equal to 40, then convection, natural convection, may occur. So you can look at the thermal data in some aquifer, and depending on this condition, suspect eventually that you may have some release of heat or transport of heat through natural convection. Here, this is just to show that the critical thermal gradient needed to have thermal free natural convection depend on the aquifer thickness and depend also on the permeability. Here you have different permeability to reach this value. So for instance, for let's say a classical thermal gradient that we have in the Earth around 33 degrees per kilometer, typically you are around here. So which means that if the permeability is relatively large, around typically 1 Darcy, then if the aquifer thickness is around 600 meters or 1 kilometer, free convection may occur. If the permeability is lower, of course, you would need a greater thermal gradient. So, after this brief introduction, let's speak about a bit about heat transport in fractured rock. So, the main thing about fractured rock is that the size or the scale of the heterogeneity is typically not the same. Here you can have meters or decameters or kilometer scale heterogeneity, and in that case you cannot assume that you have a thermal equilibrium between the fluid that passes through the medium and the rock matrix. And in that case, what you expect is more to have advection, especially if the permeability is low of the rock matrix, than to have advection in the fracture and some conduction into the matrix. And this is something that we have to look at. And the problem is that if we can look at it relatively easy in some simple model with regular fracture size, for instance, but in natural system, such like this one, this may be much more difficult to assess. So, typically, the application there are less geothermal application for the shallow in fractured rock, for the shallow aquifer, but it's more typically for what is called, for instance, enhanced geothermal system, where the idea is to go to look for some deep geothermal resource and deep geothermal resource in what we call some hot dry rock, which may be non-permeable, but whose permeability may be enhanced. And then, in that case, if the permeability is sufficient, we may have an injection borehole and production borehole that allow to take the heat from very deep system. But in that case, we do not expect, we shall see, we do not expect especially some kind of homogeneous or regular system. And then the question is about what is the role of the heterogeneity of fracture network. About fracture fault of joint, I will just present few things about what we call fracture fault joints, etc. So typically, this is some photograph or some example of fracture and faults. Here you can see that there are many fractures. Almost, in some cases, it's almost regular. The scale is given by the hammer here. Here you see another example about what we call faults. There is these little arrows, and this little arrow indicates that there has been some shearing, and these are some small faults. Here this is a road, and the scale is given here. And here what you can see is an even larger fault. The scale is given here, and what you see is that here this is what we call the hanging wall on the foot wall. On the two parts of the rocks slide on each part, but between, in the fault zone, you can see this material. And this material is not this one, but it has been transformed. It's typically what is called a gouge, and it may modify strongly the permeability of the medium. In addition, what you may have when you describe fracture on faults is that in some case you have what we call a fault curve, but in a side of each fracture you may see few fractures until you reach the intact rock. So in fact faults do not develop only by themselves, but they develop also what we call a damage zone around the fault. So this is typically what has been described here, the fault core that may be more or less permeable, but some fracture around that may allow for permeability of the system. This has been conceptualized by geologists, and for instance here you see typically what you can have depending on how well developed is the damage zone and how well developed is the core. So typically you may have what is called a localized conduit, which may give rise to a permeability, but it's a very localized system. But if the cores, because the material inside is broken and typically the size of the material here is really reduced, then in that case it can give rise to what is called a localized barrier. So instead of having something permeable, you will have something impermeable, at least perpendicular to the fault zone. And depending also on the development of a damage, you may have some permeability around these conduits or around this localized barrier, which would allow fluid to flow. Another way, or just to give some complement to that geological view about fracture, fault, and zone, here this is typically what happens when you have a joint, which is just an opening, and then in that case it can give some permeability because you just open, while we saw that when we have shearing, then we reduce the size of the element inside, and there is the creation of a gouge that may be less permeable. And in addition, it is also well known that, for instance, in sedimentary rocks, what you can have is some phyllosilicates like the clays that just fill into the fault zone, and that leads to what is called clay smearing. And in that case, you would have something that is much more impermeable and that will not allow to have, that will lead to a compartmentation of the system and not something really permeable. So that was just an overview about where come from fracture very rapidly and how we can see or conceptualize permeability structure, at least in some environment. Here this is unlithified or lithified siliclastic rocks. And you can see that in that case it's very localized deformation, while here you have more damage all around, and then what you expect as a permeability is a more permeability developed within the fault, while here you may have some permeability development all around the fault zone, depending on the geology and the condition. Now, the question is how this may be this information may be used in our case, and usually in hydrogeology what we have is much less information about the geology because we have just some borehole. In the base case we have some cored boreholes, but it's difficult from this information to go back to this system and have really apply this conceptualized permeability structure. And typically this is one example. This is one example where we are working at the plumber site, and for instance the plumber site, this is simply a granite. We are at the roof of a granite, and this is mica schist, and the contact zone between mica schist and granite, this is a mylonite. In geology, this is what we call, there is some mylonite, which means that there is some very localized deformation, and at relatively at a depth about between 5 to 7, 10 kilometers maybe. But there is very strong deformation that appears here. There are some secondary normal faults. You can see in the field very well deformation, but when you look at the data in terms of hydrogeology, for instance, this is one borehole, and the borehole has been cored. And when we look at the ambient flow, which is some data that we have from typically a flow meter, what we see is, as Bess mentioned, typically we are in crystalline rocks, typically we would have 3 to 4 major inflow or outflow. But to relate this flow zone, this is at each step, typically we have some permeability change, but to relate this permeability change to the geology and to know where this gets from, it's really difficult. Also here, for instance, we see that this is typically a fault gauge that was very well described from the core, but we don't see very well the corresponding permeability around. And in fact, the permeability we found, at least in the small scale, is typically linked to some fracture that seems more or less sometimes erratic. So we know typically that in this environment we would have a greater probability to find some permeability around the major structure, but after, to do a link between deformation and permeability is really difficult. So that's that's one of the difficulties. So since we cannot rely, we need to use it, but we cannot rely only on geology, then what we can do is to do some field measurement. As Bess also presented some field measurement to characterize the flow property of fractured rocks. So what I will speak about is mainly some methods. I will just present in few slides some methods that are used typically, and just to show up to which point we are able to image the property of the medium. And, but what I will present is mainly applied to crystalline rocks, which means that the permeability are coming from the fracture and not from the matrix, which is typically impermeable. So the first, of course, the first method you can apply in such system, but you do not learn so much about heterogeneity, is typically a pumping test. And for the pumping test, it was just to remind that there is of course the classical solution, but the diagnostic plot on well test interpretation, there was a review paper from Philippe Renard recent in 2008, and which showed that for different cases, you may have different boundary conditions, you may have different property of the medium, and this approach, which consists on working on the head variation, but also the derivative of the head variation, helps very much to understand what could be the boundary condition and what could be the type of the medium you may have. In fractured rock, for instance, often what is used, even we can discuss about that, but it's typically the double porosity medium when the matrix porosity has some permeability. So, but typically this approach allows you in some case, if the permeability is enough to characterize somehow the boundary condition on the overall permeability. However, this gives you only an overall permeability of the medium, and it gives nothing about the permeability variation in the medium. And if you need to predict transport, you need to have some information about that. And typically, in that case, what you can do, there is different methods, but often what is used is Packer testing. Maybe Jan Olof, you will speak about that a bit, but it's typically you can do some Packer testing with different separation for the chamber, and you can do some hydraulic tests, for instance, do some slug tests, some injection tests, different kind of tests to infer the permeability. And then you can have, this is relatively easy, you can have some idea about the permeability in crystalline rock, like for instance here this is the number of value for the different permeability that has been measured. So what is really impressive is that in that case, it was in Aspo in Sweden, in that case there is a very large range, large distribution of permeability. This is the first observation, and from that it's difficult really to, you have the distribution of permeability. You may have some, this is another example from Mirror Lake, and here also you can see that at several meter scale the approach was the same here to measure the range of permeability is really large. If you do some measurement at the 100 meter scale, usually the variability is reduced, but usually also you do not have so much, it's more difficult to do this measurement. And then here they did a model to infer the permeability at several kilometers, and then they deduce this conceptualized model. So you may have from this measurement and from cross-borehole test, you may have some idea about the connection between the different boreholes, but after, when you rebuild this is typically what we call the conceptual model, but it's not really what we would like, an image model of the site. So this is one main limitation. For the last 15 years, for instance, we had hydraulic tomography also development, and it was really useful is the fact that you can, we spoke a bit already about that, you have some, for instance here, you can do some testing and record the variation at different depths, and from that if you repeat all this testing at different depths, then you can try to reconstruct the property of the medium in terms of hydraulic conductivity. But one main limitation again here is that we see here, this is the high permeability zone, is that we do not have really an imaging of the fracture, but more of the main connectivity zone, which is far to be announced, for instance, to predict transport. It's relatively limited. So just to summarize a bit what we are able to do in fractured rock hydrology is it's relatively simple to get some permeability estimate. It's relatively also simple to have some idea about the connectivity between some borehole. This is something that we can do, but it is much more challenging to image flow paths or to predict, for instance, transport just from hydraulic data. This is one of the main limitations, and we do not have so much idea about what's going on between boreholes and what's the type of heterogeneity. So we need, there is a need to combine this information with other tools. It may be hydrogeophysics, it may be also tracer test. And so I will speak mainly in the rest of the talk about tracer test and how you can combine the information from typically solute and heat tracer test to give some idea about typically the kind of heterogeneity we have behind this system. So I come back just to the to heat transport in porous media, just to just to remind that we have an advective term, and one of the questions we may ask first is, when do we have this advective term that may dominate conduction in the typically in the upper crust, on which condition? Of course, here we are pumping, but on natural condition, should we have the advection that dominates conduction, and for which condition? And for that, it has been shown, for instance, so it's simply a condition about the permeability. So the permeability needs to be sufficiently high, otherwise you will be dominated by conduction. If the permeability is not that high, but the hydraulic gradient is sufficiently high, then in that case you would have advection of conduction. So typically this is the classical scheme that Ferguson et al. Did to resume where you expect to have advection and conduction. There are others. There are other presentations. Here you can see the variability, the variation of intrinsic permeability in logarithmic scale, or the corresponding hydraulic conductivity. And typically, what you expect for advective heat transport is that you will have advective heat transport for permeability that is larger, typically, or the hydraulic conductivity larger to the 10 minus 9 or to the 10 minus 8 meters per second. So, on this has allowed to use heat as a ground pressure in many applications. I will just show a few examples. So this was some simulation done in the 70s. There are also some, for instance, you can refer to the review from Mary Anderson about heat as a groundwater tracer. Typically, the idea is that normally we should temperature should follow the geothermal gradient, but if there is groundwater flow, then there should be a deformation of this geothermal gradient, either one way or another, depending on if you are typically in a recharge area or a discharge area. So that's typically what is used in general. So on this, for instance, I just show an example that comes from North Alaska, and it's an example from the et al. Where they measure, in fact, temperature at sufficiently great depths. Here you can see that it goes up to 600, 1,000 meters deep, and what they show is to measure from the Brooks Range along the cross-section here toward the low altitude terrains here, and here is the Arctic Ocean. And what they were showing is that the variation with depth of temperature is really varying from the Brooks Range up to this to here, so that in fact you can measure the heat flux. The heat flux is just the product of the conductivity times the vertical thermal gradient, and they were able to show that there was really an anomaly of shallow heat flux here coming here that they explained by large-scale groundwater flow. Large-scale groundwater flow flowing from the Brooks Range up to the coastline through maybe some aquifer, but this with the large-scale groundwater flow. This is one example at large scale. But we can use it also at small scale, and for instance, to infer, for instance, groundwater flow in borehole. Typically, when you have long screen borehole or open borehole, you do not expect to have the hydraulic head to be exactly the same at all depths, typically because you are either in recharge area or in discharge area. And in that case, if you have the hydraulic head that varies according to the depth, but in that case you would have some flow in the borehole, and due to that flow you can usually use heat or temperature very easily to track this flow, and you have several examples here that show that if you have, for instance, some fracture, then you would have either, for instance, upward flow, you would expect some deformation of the temperature, variation with depth, that will reveal you the presence of inflow or outflow that are easy to interpret. You can also use or activate the system, use some active tests. So instead of using it as a passive tracer, you can do, for instance, some pumping test and just follow or monitor the temperature to really monitor the groundwater flow. This is some work that we have done in a karstic aquifer. So this is not typically a fractured rock aquifer, but we have typically the same level of heterogeneity or even bigger. Typically in that site, what we expect is 3 levels of main karst. This is seismic imaging through seismic velocity imaging. So one level at 30 meters or 50 meters, one at 85, and the deeper one around 105 meters. And what we did is to monitor temperature with fiber optic DTS while we were pumping in that borehole, and we installed the temperature monitoring in this borehole. So that's the borehole followed, but we did that in many boreholes, and it allows us to really understand what are the temperature change and what are the flow change and flow connection between the pumping borehole and the observation borehole. Typically, what we observed here is the temperature scale is here from low temperature to higher. So this is typically 12 to 13 degrees. And this is before pumping. And as soon as we develop some pumping, we see discharge, which is typically because this inflow will feed the lower fracture zone. And what is interesting with the fiber optic DTS is that you can really follow in real time what is going on and the change in temperature through time. And so it gives you typically the velocity of the borehole flow that you observe through time. So this is one way of using heat as a passive tracer when you do some pumping tests, for instance. But another way would be also to do typically some thermal tracer test and to inject heat and to follow this heat change. This is what we've done in one site here, and we were interested by the transport of heat from here, the injection, toward the observation well here that has been monitored also thanks to fiber optic DTS. So we were pumping here, so typically we inject heat at 50 degrees while the ambient temperature is around 15 degrees here, and we recover the temperature in the pumping borehole. So typically what we obtain is this this variation of temperature with depth. This is depth and this is time. This is so the experiment lasts from almost 1 full day, 20 hours. And what we observed is that it was transported from here to this borehole, and we could see very well one heat arrival here at 80 meters depth, another one at 60 meters, and then above something like 58 meters, we don't see any warm arrival, simply because here we have some cold water arrival that dilutes the signal of heat. So what is interesting is that we see very well these two fractures. What is also interesting, that was the first time we did that, we wait for 20 hours. Usually in that experiment, if we have a solute tracer, it typically takes half an hour to 1 hour to go from here to here, but here we just have an increase of a few tenths of degree. Typically it's about half a degree or 1 degree maybe the increase of heat, which is relatively low, simply because most of the heat in fact diffuses or is conducted into the rock matrix. The other interesting thing is that there was, when we compare to some flow log, we see that we knew already that this fracture will carry flow. We knew already that this fracture will carry flow. So we identified, well, which one is connected from here to here. So this is fine. But for instance, from the flow log, this is a flow log, here we do not see this fracture. So it seems that some fracture that carry very little flow, that cannot be detected with classical flow meters measurements, may carry some heat. And maybe even the one that carry the most heat. So with this in mind, we were interested to work more on heat transport in fractured rock. So I come now to my last, yes?
Can I ask you about the experiment before?
Yes?
If your borehole is like sealed with, not sealed, but the surrounding is metal, don't you have like a lot of heat transfer through the metal and you have it all along the line?
All along the line. It could be, if it would be the case, yes, but here it's open borehole. So what you have is just the rock matrix all along. So we were interested about heat transport in fractured media. So typically what we have to solve, and the question that we have to face in fractured media, is that there are typically what we call two scales. One scale is what is a fracture, because the fracture we always say it's open, it may be a plane and so on, but in reality this is a representation about the heterogeneity within a plane, that of a plane of a fracture, but you can also discuss about that with Yves, for instance, who did a lot of work on the heterogeneity inside of a fracture. So it's not a plane, it's more something that has a given roughness on where it can localize, in fact, and give rise to flow channeling. The other thing is that the network by itself may be at some place more or less regular, but maybe also very regular, and you may have some complexity at all scale. So there has been some numerical tests to show that, and typically this is the work of Neuville et al. And what they did is to consider a rough fracture, and they did a thermal pressure test inside this fracture, and here you see the temperature field. And you can see that, compared, this is not surprising, we see that where the aperture is relatively large, there are more extents of the temperature inside the system. So this is not surprising, but what they were able to show is that the exchange with the matrix, in that case, it's much less than expected, and in fact it allows to remain the main heat transport within some kind of channel. So this was at the fracture scale. Similarly, there has been also some other work, but at the network scale. This is just 2D experiment, but considering a fracture network that has been mapped. This is a natural fracture network that has been mapped and then used for numerical simulation. And here, heat was injected on one side and was traveling toward the other side. And in the similarly that at the fracture scale, what we see is a lot of channeling, which means that heat is not distributed over the whole system, but just remain localized or channeled within a subnetwork of the fracture and of the permeable fracture. So, some other work to show if, or to test if this is important or not. 10 minutes? Oh, I should hurry up. Thank you. So some other work that has been done, but now considering depth, here you can see that the pressure and the stress are really large, and they just simulate a kind of EGS with an injection borehole and a production borehole with one fracture in the system. And with this fracture, they consider it either as a plane or as with an heterogeneous aperture distribution, which have a given correlation lengths. And what they were able to show is that here flow is more distributed, which is what is expected, while here, for instance, this is the flow here, while flow here is more localized or channeled. And this is the first observation, and the second observation is also that thermal stress enhances channeling, which means in their work what they were able to show is that through time the aperture distribution varies because of the thermal stress, and this affects also the channeling. And what is interesting is that if you look at the production temperature, what told you this morning, Peter, the production temperature through time. Here, this is the production temperature at the beginning, 200 degrees, and through time from 0 to 30 years. What they were able to show is that if you consider an homogeneous aperture field, then the temperature will decrease, but decrease will slightly. But if now you consider an homogeneous aperture field taking care of the thermal stress, then the decrease will be much stronger. And if now you consider that it is an heterogeneous aperture field, then in that case, it can lead to a strong decrease, and then the life expectancy of this system is really dependent on the aperture distribution, on how it evolves through time. So the question of channeling is really an issue, but the problem is that there are not been so much data. So what we did, and now I have not so much time to present that, what we did is to do two types of tests. Push-pull thermal tracer test, when you inject heat and then you pump the heat back to the borehole, and when we did also some cross-borehole thermal tracer test. We did typically this type of test to bring some data and to show also what kind of model should we have behind, and we compare solute tracer test with thermal tracer test. So this is the field. This is typically, so I will skip that. This is typically what we observed. In blue, this is during the push-pull tracer test experiment. And in blue, this is the solute tracer, while in red, this is the heat, which is recovered earlier because it's the fracture the matrix that have been heated that give back the heat when we pump into the fracture. And we did some theoretical development considering some very simple geometry, one fracture or a channel or a set of channels, and did some numerical modeling. So this is typically the thermal breakthrough we obtain. And what is interesting is that when we look at the scaling through time, this is time and this is the normalized temperature, it follows in fact not what is classically expected when it's conduction and diffusion which operates, which is T at the power minus 1.5, but it follows very well this scaling that we found that correspond to much more a channel or a channelized. So in other words, when you do some push-pull, then you may have some insight about the geometry of the main geometry about your fracture system, which is either fracture with the flow dispersed into the medium or a simple channel. We did also some cross-borehole thermal tests. The only thing is that since we saw already that sometimes from one borehole, other borehole, it takes days or a few days for heat to travel, because most of the heat you inject will be conducted in the matrix. What we did is what we call a single well thermal test. We put a double packer here, and we were pumping above in this fracture. And what we wanted is to have a thermal tracer test going from this fracture to this fracture. So this is typically what we do expect. We inject heat here into the chamber here, and while we were pumping above, and we get the temperature change just right here. We'll not go too much into the detail, but we did in the meantime some analytical development to know how typically would scale or would depend on the parameters, the thermal retardation and the peak amplitude attenuation. Typically, when you have a solute and when you have heat, what you expect is an attenuation of the peak, but also some thermal retardation. On considering some geometry, we look at the how, depending on the aperture and depending on the time of advection, could be defined the peak amplitude and the thermal retardation. And what we found that is interesting is that the scaling of the peak amplitude is not the same for this geometry or this geometry with each channel. So we did, this is an example of the thermal tracer test we did. This is, we monitor with fiber optic DTS. This is depth above the packers. This is time again. On what we see, this is the injection. When the injection appears, we have few leaks here, but it is removed very quickly. And after, since we are pumping, we see that this cold water arrival. And then we have this heat increase, which is typically corresponds to our tracer test that was injected here and that is found here. So we typically, this is the temperature signal that we are now able to compare with the solute signal. And what we found is that the thermal retardation is relatively short in that case, and it's only around 15 minutes. And we use some modeling to try to model and to see if it was consistent with one fracture or one channel. And when we consider, for instance, one fracture, we can very well model the solute transport. But in that case, if we take this fracture aperture, with the time predicted for heat to be transported is about 18 hours, while we observe something like in 15 minutes. So in that case, it's not possible, and we need to have flow channeling, because when you have flow channeling, you restrain the amount of heat that is conducted into the matrix, and indeed, when you consider a channel, you it's possible to model both solute and thermal transport, which show that it seems that the system is really well channelized in the system. So I have almost finished. We did also some other thermal tests, and what is possible is that since the tracer test we vary the advection time typically, we can look at how the peak amplitude is attenuated and for the different tests and compare it to the model. And the model that fits nicely the data, also we have mainly 2 points because we have 2 pumping rate, is typically the model that follow the channeling. So to conclude, it seems that in fractured rock, flow channeling may be really an issue. This is not, we are happy because it's not so easy to show that channeling affects from data thermal transport. We can have some models, but here we were happy to confirm that from some thermal tracer test experiment. And the interest is that it's control not only the breakthrough time or the life expectancy of deep HDF system, for instance, but also the physics of heat transport, because if typically you have a channel, you would have a radial conduction around the channel, while if you have a fracture, you would have only the conduction perpendicular to the fracture. So this, the heterogeneity really matters when considering heat transport. This makes sense, but as was saying Peter this morning, it's not usually taken into account. But on the other hand, what is nice is that heat may be an excellent tracer for characterizing the type of heterogeneity and try to give you some insight about what's going on in the medium and how heat is transported in the system. So just a take-home message also is that in the field, experiments at different scale are really useful to constrain the physical processes. If we would not have experiments at different scale, if we would not be able to look at the scaling, that would be much more difficult to constrain the underlying physical process. And just a last take-home message is to say that to do field work, you need to have the enthusiasm of Johns, but you need to have also the well-defined objective of Niklas, and this really a combination of both. And I'm just thinking about the fisherman analogy when you are somewhere lost in the sea. Normally, a fisherman knows where he goes, otherwise he has a poor chance to get fish. So typically, the distance were short. It's about few meters. And typically what you do before doing that experiment is that you do some solute tracer just to make sure that you are well connected. For instance, for this one, we had already done some tracer test experiment, and we knew that the tracer test would take typically for half an hour, 1 hour to go from here with this pumping rate to this pumping rate, and after we did some thermal tracer test. But it's typically, on the side here, it's typically 6 meters from these two boreholes, 10 meters from the other one. And the problem with it is that it's nicely give you some insight about the heterogeneity of your system, but you lose most of your signal. So if you are too apart, this is good for production, but this is bad for experiment, I would say.
Shallow length, that's also bad for efficiency if you actually want to produce electricity or heat, right?
Absolutely, absolutely. When I say channeling may be really an issue, it means that I don't know how much we can extrapolate what we found on the Plummer site to deep underground, because we have something, the fracture are relatively well open on the channel, are already also some really open channel, and I don't know in geology where they come from, but it's exactly the consequence of such channeling would be for deep hot dry rock or EGS would be to have shortcuts, and then since you inject cold water to have hot water, then to decrease the efficiency because you have a rapid, you would have a more rapid transfer of Absolutely, absolutely. On the surface, this is because you have much less surface area because you have radial diffusion compared to perpendicular diffusion, and then the system becomes less efficient.
Do you want to take those questions from the back? Oh, you're the one in the back.
Thank you for this talk, Olivier. And you know, I'm also a fisherman, and you know this saying that the only time the fisherman has a truth actually is when he says the other fisherman is lying. Okay, I mean, not everybody understands that. Fishermen, fisher ladies. But I mean, the question I have, because I've also been working on thermal tracer testing, but the things that I've been asking myself is actually not just the question of how much I see in these breakthrough curves when I look at the rising limb, but the question is what I see in the declining limb if you have in the breakthrough curves, if you have these pulse temperature signals that you inject in your system. In other words, to what extent in your interpretation are you using the late time temperature signals? Or in other words, from your expertise, how much would you expect information content in there from the release of heat after heating your system?
So for the push-pull, typically what we use is the time of the peak, the scaling of the time of the peak, but also the scaling which is different and which depends on the geometry of your heterogeneity. So typically you can use both information, and it's true that the late time scaling is also very informative about the conduction process depending on the geometry of your heterogeneity. So that's for this. We were not able to do the same, but this was mainly because here For the cross borehole, we had some, where it is, we have some, where it is, we have recirculation. We have recirculation, which means that in that case it's much, but normally we should be able also to use the long-term scaling to give some insight about your heterogeneity on how it looks, what type of heterogeneity do you have. When you use solute, typically you have a nice, and the advantage is that it's conservative, you have a nice signal, but the problem is that you can model that either with a fractured plane, either with a channel, and it's not, you cannot decipher which model. While when you consider both the solute transport and the heat, then you can know what is the type of heterogeneity that makes the transfer.
So two questions. The first one, using heat tracer, you will have a different the fluid viscosity will change due to the increased temperature. How strongly do you think will affect that result? And the second question would be, due to thermal expansion, you will change the fracture network that you're currently investigating. How strong will this actually lead to wrong conclusions on the original fracture network?
Typically, here we didn't look at the change. It may affect, and it's true, because there is a viscosity dependence, for instance. We didn't took that into account, but typically here you see the amount of heat that is carried is not that different. It's here we reach something like 18 to 19 degrees, while the background temperature is around 15 degrees. So there is not that much change in temperature, at least on the recovery borehole. On the injection borehole, we inject something which is much higher. This is true. But since we expect that most heat is lost here through conduction, we neglect that. But it's for sure that for the simulation I show you also for the deep underground system, and they didn't, if I'm correct, they didn't took into account this variation, and they admit it, if I remember correctly, and it may really affect, because the change of temperature may greatly affect viscosity, and then the capacity of heat transfer will be evidently much greater.
We have time for a very last quick question. I might have a question that stretches it really far, actually, until tomorrow's topic. So, as far as I understood, you can't actually estimate the roughness, or have at least some idea about
some rough model of roughness.
That's what the way. And can you correlate that knowledge somehow to a mechanical stability of the fracture in terms of moving with some stress conditions, induced seismicity, stuff like this?
I would be interested to redo the same kind of experiment, but for measuring carefully, not this time where it is the temperature change, but also have some fiber optic. If it's possible. It's not easy to have a whole contact with rock, but you may measure the deformation through fiber optic, and in that case to look at what would be the thermomechanical effect how it can affect. But for the moment, I don't know how this will react.